Okay, so good morning. And today we are going to build up our convolutional neural network from the first principle, starting with the basic convolution operation and ending with the AlexNet. That was all is the content of the unit 2. Even we have by the end of this complete unit, we will be able to explain not just what is the concept, but it is like why it is needed and like how the every idea got evolved. So I want you all to think of this lecture as one of the continuous chain of a problem and solution. And how who has invented convolution, pooling, or the AlexNet design choices, etc. And each one exists because something were broken before that under the real world condition. So the new technology or the new evolution has come into the market. We'll see the agenda. So we will be covering. So we will be covering with the problem as like why plain neural network fail on the images, and then the convolution operation with a work example, then parameter sharing and equivalent representation. We have the pooling, the types and the worked example, then the variants of the basic convolution function, the basic architecture of CNN, and then the AlexNet, the architecture that started in the deep learning. So this was all about the agenda of the unit 2. Now let's see the most important crux. That is, why do we require the CNN? I hope you all are able to see the screen. Let me check again. Okay. So now you must be able to see the screen of the why we require CNN. So let's start with the problem. A plain neural network, which is my artificial neural network, which is also called as ANN. It takes an image, flattens it into one long list of the numbers before feeding it in. And looking at the left card, if we take a standard 224 by 224 color image, that is three color channels. Flattening gives us the 150528 individual number. Such a huge number we are getting through this. And then now suppose the very first hidden layer had just 1,000 neurons. Then every one of those, that is 150528, that is my 1,50,528 inputs, connects to every one of those 1,000 neurons, which gives us over 150 million weights. And that's for a single layer of network. I hope this is clear with all of you. So now let's go deeper on why this actually hurts, right? So till now we are saying that, okay, huge numbers of the input size is getting generated and every input is going to get connected with the all neurons which are available over there. But then now let us see like what is the problem? Just by looking at the raw parameter count, we will not be able to understand what hurts actually. So first think about what flattening physically does. It takes a two-dimensional grid where the pixel 10 by 10 is right next to pixel 10 by 11 and forces them into one dimensional list where they may end up hundreds of the positions apart with no signal to the network that they ever were ever neighbors. So the network has to relearn from the scratch through the millions of training examples, something that is simply given for the free in the structure of an image. So that nearby pixel tends to be related. And that nose or edge is a local pattern, not something scattered across the whole image. Now, second, think about what happens if the object in the image moves. Correct. So if a cat shifts 10 pixels to the right, almost every entry in that flattened 1,50,528 length vector changes. The dense layers were tuned, assuming that cat's pixels sit in the specific positions. So a shifted cat essentially looks like a brand new, unseen input to the network, even though visually nothing about the cat changed except its position. So this is the deeper reason dense networks generalize poorly on the images. They don't have any built-in concept of the same pattern. They just move. Now look at the right card. A CNN instead uses a small 3 by 3 filter with three channels. Right? Now that's only 27 bit, right? You can see at the right we have the CNN with the 3 by 3 filter, correct? And three channels. So it only weights of the 27 and it reuses that same filter across the entire image. That's over 5.5 million times fewer weights for the equivalent layer. And because the filter slides across the image rather than being applied to fix specific pixels positions, the spatial structure is preserved instead of destroying it. So this massive gap is the entire motivation for everything we will be covering today. I hope you have understood the motivation for the CNN. So ANN flattens the structure. It converts it into one dimensional. But what happens in the CNN? It considers the dimension. It considers the channels also. So this gap is the entire motivation for everything we are covering in the unit 2. So every concept from here onwards is really just an elaboration of this one core idea. Build a network whose very structure understands that images are spatial, local, and repetitive. This is what is the basic concept which we will be learning over here. Right? So now move to the convolution operation. What does exactly this convolution operation do? And what does all these terms stands? So the convolution operation is a small filter, which is also called as a kernel, which slides across the image. At every position, it multiplies the overlapping values element by element and sums them up, producing a single number. So this is done at every position and we get the feature map. Again, I will repeat what is this convolution. So the convolution is a small filter, which is also called as a kernel. This slides across the image. At every position, it multiplies the overlapping values element by element and sums them up, producing a single number. And this is done for the every position to get the feature map. That's a simple way how the convolution is defined. Okay, give me a time. I think this is not getting. Okay, I will again share it. Okay, here I think you are able to see this convolution now. Right? So convolution slide. So again, I will repeat what is this convolution. Convolution is a small filter which is called as a kernel, which slides across the image. At every position, it multiplies the overlapping values element by element and sums it up, producing a single number. And it is done at every position, and so we get the feature map. Now let's build a real intuition for what this multiply and sum operation is actually doing mathematically and conceptually. Right? So each filter is essentially asking one specific question at every location in the image. Like, how much does this small patch of image sitting under me right now resembles the pattern I am looking for? So the filter's weights are that pattern. If the patch under the filter looks similar to what the filter is tuned to detect, the multiplication summation produces the large value. If it looks completely different, the value comes out small or even the negative. So a feature map is really a map of where is the image does this particular pattern appears and how strongly does that pattern appears. This is fundamentally the difference from the dense layers weighted sum because a dense neurons look at entire image at once and ask a single global question like whereas a convolutional filter asks the same local question repeatedly at every position. So this there is a difference. I hope you have understood what does this actually the filter means and what does it do on the every image. So the size of that output is governed by the formula. The formula is n minus f plus 2p divided by s plus 1, where n is the input size, f is the filter size, p is the padding, and s is the stride. Now let us understand what does this formula says. The filter needs f pixels of a room to sit inside the input. So after placing it in its very first valid position, there are exactly n minus f remaining pixels. It can still slide across. Dividing by the stride tells us how many discrete steps fit in that remaining space. I hope this is clear. And we add one back because we are counting the starting position itself as the first valid output. Now, padding P simply adds the extra border pixels on each slide because this calculation effectively growing n to give the filter more room to move without shrinking the result. Now, let's define the four terms. We'll keep hearing. The kernel or the filter is a small weight matrix that slides across the image. The stride is how many pixels it moves at each step. The feature map is the complete output produced after sliding over the whole image. And the receptive field is the region of the input that influences a single output value. So this is last one matters enormously later because we stack more convolutional layers. The effective receptive field of the deeper neurons grows. So letting them see larger and larger regions of the original image, even though each individual filter is still small. I hope this is clear with all of you, like all these terms. Again, I will repeat these terms. The first important part, what we have seen is what is the role of the filter. So again, I will repeat that each filter is essentially asking only one specific question at every location in the image. The question is how much does this small patch of image sitting under me right now resembles the pattern I am looking for. So the filter weights are the pattern. If the patch under the filter looks similar to what the filter is tuned to detect, the multiplication summation produces the large value, right? And so a feature map really a map of where is the image does this particular pattern appear and how strongly. Right? Now we will look like why it is different from the dense layers weighted sum because a dense neuron looks at the entire image at once and asking a single global question like where as the convolution filter asks the same local question repeatedly at every position. I hope this concept is clear. Now the second concept we'll look into the formula. Now what does the formula says? Right. Now, what does it say is the filter needs f pixels, f number of pixels of room to sit inside the input. So, other placing, it is very first valid position. Now, there are exactly n minus f remaining pixels. It can still stride across. Dividing by the stride tells us how many discrete steps fit in that remaining space. And we add one back because we are counting the starting position itself as the first valid input. Now, padding P simply adds extra border pixels on each side before this calculation, effectively growing n to give the filter more room to move without shrinking the results. Clear? I hope these two things are very much clear to all of you. Now we'll see the working example of this. So moving ahead, let's look at the working example. So we will see here the sliding filter. I hope you are able to see it on the screen. So let's make this very concrete. Here is a 5 by 5 input matrix and 3 by 3 filter with the values 1, 0, -1 in every row. You can see it over here. Right? Now watch what happens when we take the highlighted top left 3 by 3 patch of the input and multiply it element wise with the filter. Then sum everything up. So row by row. So 1 times 1 plus 2 times 0 plus 3 times -1. Then 0 times 1 plus 1 times 0 plus 2 times -1. Again, then 1 times 1 plus 0 times 0 plus 1 times -1. So this gives us -2 plus -2 plus 0, which is total value of -4. Now, what does this -4 base is? This -4 becomes the very first value in our output feature map. Okay. Now let's pause over here and really understand what does this number minus 4 tells us. Now, what does this minus 4 says? It's a large magnitude negative number, which for this particular filter means the patch of the image under it had a strong left to right pattern where values decreased from left to right, or more precisely, where the left side of the patch was brighter or higher valued than the right side. Since the filter rewards high values on the left with the positive weight and penalizes the high value on the right with the negative weight, if we keep sliding this filter across all the remaining positions, we had fill in the rest of the 3 by 3 feature map. And wherever this exactly left, bright, right, dark pattern repeats in the image. So we had again see a large negative or large positive value depending on the direction of the transition. So we can notice over here, notice the pattern filter itself. It is having the plus one on the left column. The filter has the plus one on the left columns, minus one on the right columns. This means that filter produces the large magnitude value, whereas their sharp left to right changes intensity. In other words, the specific filter is a vertical edge detector. This is the concrete meaning behind the phrase that filter learns a pattern that you will hear constantly in the deep learning during training. So the network doesn't get handed a hard-coded edge detector like this one. Instead, propagation and gradient descent gradually adjust these 9 numbers so that the filter becomes so good at detecting whatever pattern is most useful for reducing the network's overall error. In a training network, the very first layer typically discovers the filters that look like the edge detectors, similarly to this one, entirely on its own. So simply because the edges are such fundamentally useful building blocks for recognizing more complex shapes later in the network. Again, I will repeat. Please look here at the filter. Now, this filter, how does the filter looks like? It is having the plus one on the left columns and minus one on the right columns. What does it mean? The filter produces the large magnitude value, whereas there is a sharp left to right change in the intensity. In other words, this specific filter is a vertical edge detector. This is the concrete meaning behind the phrase. I hope here it is clear till now. So there are no questions, and I will like to stop over here, and we will be looking into the other remaining part, other types of the convolution and etc. in the next lecture.